Sathyabama Institute of Science and Technology.
A very warm welcome to all the listeners watching this topic, antenna array. So this is what the topic for today's discussion. What is antenna array or define antenna array? So to increase the field strength in the desired direction with a group of antennas excited simultaneously for a particular direction. So such group of antennas are said to be antenna array. Let's see about the antenna array introduction and where it is used and what are the application of antenna array, and if two antennas are excited simultaneously, what's the outcome of that particular antenna, and then if number of isotropic sources or antennas are increased, how the radiation pattern will be. So this is what the overview of this session. So let's see one by one. So antenna array to increase the field strength in the desired direction by using group of antennas excited simultaneously. Such a group of antennas are said to be antenna array. So to improve the directivity and to increase the field strength, we are going for this antenna array. So to enhance the signal quality, the antenna array is used. And in applications such as point-to-point communication, long-distance communication, and also in radars, communication, and in broadcast applications, we need such antenna array. In radars, communication, and broadcasting, a beam forming technique. So beam forming is nothing but increasing the directivity or the field strength in its desired direction, which is the application of radars, communication, and broadcasting systems. So now the array of 2-point sources. When two antennas are excited simultaneously, what are the configuration will be appearing? So with respect to amplitude, with respect to phase, equal amplitude and in phase configuration, equal amplitude and out of phase configuration, and unequal amplitude with any phase, or the three configurations we are going to discuss one by one. So array of 2-point sources with equal amplitude and in phase direction, in phase configuration. So this is what two antennas excited simultaneously. The outcome of the radiation pattern will be a bidirectional pattern. So two antennas, consider 2-point sources having equal amplitude and in phase. Distance between the 2 points are separated with a distance of d, and phase angle between 2-point sources is said to be psi. We are going to see some numerical calculations, and by means of this we are going to find the outcome of 2-point sources with equal amplitude and in phase configuration. So to get the outcome of the radiation pattern, we need to analyze what is the path difference between the two antennas, and phase angle, what is the phase angle difference between the two antennas. So the path difference is equal to d by 2 cos theta plus d by 2 cos theta, which is equal to d cos theta. When it is included with wavelength, it is d cos theta by lambda. Next, step 2, that is phase angle difference. Angle psi is equal to 2 pi d by lambda cos theta. So 2 pi by lambda is nothing but beta. So beta d cos theta is angle psi, that is phase angle. Next, we are going to analyze the electric field strength of the two antennas. So first field strength, first antenna is it is having an amplitude and its phase, and second antenna is having its own amplitude and phase. The total electric field of 2-point sources is the vector sum of individual elements, that is the total electric field ET is equal to E1, that is E1 and E2 are amplitude of point source 1 and point source 2. Next, e power minus j psi by 2 and e power j psi by 2. So that is what the phase. So since the configuration we are discussing here is equal amplitude and in phase direction, so equal amplitude, because of equal amplitude, E1 is equal to E2, which is taken as E0. So the phase angle is e power minus j psi by 2 plus e power j psi by 2. So if we are calculating, finally we will get the total electric field strength as cos of pi by 2 cos theta. Next, fourth step is we are going to draw the radiation pattern. So radiation pattern, we need to draw or mark the angles which shows the graphical representation. To draw the graphical representation of a radiation pattern, we need 3 steps. So, we should find the direction of maxima. Maxima is nothing but the maximum radiation in the direction. So, that is what direction of maxima, and minimum direction, that is said to be direction of minima, and finally the half power point direction. So, first direction of maxima, we are taking the total electric field strength as plus or minus 1, whereas in direction of minima Et is equal to 0. So, when we are applying this cos of pi by 2 cos theta, that is our total electric field strength Et, we will get plus or minus 1. We are substituting plus or minus 1, whereas for minimum we are substituting 0. So, finally, when you are substituting all the values, we will get the maxima direction as 90 degree and 270 degree, whereas minima we will get 0 degree and 180 degree. So, the maximum radiation is at the angle of 90 and 270 degree, and minimum radiation is around 0 degree and 180 degree. So, finally, the third step is half power point direction. So, the point at which the power is half its value, that is 1 by 2. So, if we are substituting voltage and current, so we will get 1 by root 2. So, finally, when we are substituting pi by 2 cos theta, so we will get 2n plus 1 into pi by 4. So, the angle is 60 degree, 120 degree. By symmetry, we will get 240 degree and 300 degree. So, this is what the radiation pattern for equal amplitude and in phase direction. So, all the angles have been plotted: 0 degree, 60 degree, 90 degree, 120 degree, 180 degree and 240 degree, finally 270 degree for all the 360 degree direction. So, we will get the broadside array. So, that is what the bidirectional pattern. This pattern is said to be bidirectional radiation pattern. So, what is bidirectional radiation pattern or broadside array? So, it is an array of equal amplitude and in phase configuration where the major lobe or the maximum radiation lies perpendicular to the array axis. Next, second configuration is equal amplitude and out of phase configuration. In equal amplitude and out of phase configuration, same two antennas are excited simultaneously. As similar to broadside array, we are going for path difference. Next, the phase difference. Next, the total electric field strength. Here there is a small change because of out of phase. Because of in phase, we will calculate Et is equal to E1 e power minus j psi by 2 plus E2 e power j psi by 2. So, because of out of phase, we are introducing a minus sign here. So, because of minus, cos becomes sine. So, that is the only change for broadside array and end-fire array. Similarly, in phase and out of phase condition. So, it becomes, because of minus sign, the minus will be introduced inside. So, Et is equal to E naught e power j psi by 2 minus e power minus j psi by 2. So, Et is equal to E naught 2j sin psi by 2. So, 2j E naught is taken as 1. So, Et is sin psi by 2. Sin psi is nothing but beta d cos theta, just substituted. So, we will get the total field strength as sin pi by 2 of cos theta. So, finally, we need to draw the radiation pattern of end-fire array as like broadside array. So, the maxima radiation or the major lobe is in 0 degree and 180 degree. Similarly, theta minimum is 90 degree and 270 degree. In phase direction, the reverse operation. So, this is what the radiation pattern of end-fire array. So, half power point direction as similar to broadside array, same angle 60 degree, 120 degree, 240 degree and 300 degree is there. So, this end-fire array is an example of fishbone antenna. This is a familiar antenna, or it is said to be an Yagi-Uda antenna to increase the field strength in one particular direction. This is what the end-fire array. So, now we can define what is end-fire array. So, it is an array of equal amplitude and out of phase configuration where the major lobe or maximum radiation lies parallel to the array axis. In broadside array, it is perpendicular, whereas in end-fire array, it is parallel to the array axis. So, this is what the difference between broadside array and end-fire array. We can conclude it as the radiation pattern and the array equal amplitude and in phase configuration where maximum radiation lies perpendicular and where major axis or maximum radiation lies parallel to the array axis. So here it is in phase, there it is out of phase. Here the maximum radiation is 90 degree, whereas in end-fire array the maximum radiation is 180 degree. So we will get broadside array, it is bidirectional pattern. For end-fire array it is unidirectional pattern. So if instead of 2-point sources, if we are increasing 4 antennas, so what about the field strength? So same broadside array, what are all the steps we have followed for 2-point sources, we are going to follow. The only difference is if number of isotropic sources or antennas are excited simultaneously, maximum side lobe information will be the added point. So let's see that. The maximum radiation for broadside array, we know psi is equal to beta d cos theta, where theta maximum is 90 degree. If these conditions are satisfied, then that array is said to be a broadside array, as we discussed in n equal to 2-point sources. Here if the antennas or isotropic sources are increased, we need to find out or analyze side lobe information. So for that we are going for introduce a new formula. Et normalized function is equal to sin n psi by 2 by n psi by 2. Same as like broadside array n equal to 2, we are going to find the direction of maxima, direction of minima, half power point direction added with maximum side lobe information also. So this is what the broadside array n equal to 4-point sources. 4 antennas are excited simultaneously. So the number of point sources have been increased. So side lobes have been increased. So the pictorial representation says side lobes they exist. So as like broadside array, we are going for direction of maxima. We know if the condition is satisfied, theta maximum is 90 degree direction, then it is said to be a broadside array. So in addition with that, we are going for side lobe information. So that is what I have specified as theta major side lobe. So major side lobe, so sin n psi by 2, that is the numerical part is taken as plus or minus 1, denominator is taken as n psi by 2 is not equal to 0. So just substituting the values, we are getting the angle with symmetry pi plus or minus 41.4 degree. So now direction of maxima, next direction of minima. So direction of minima, same numerator sin n psi by 2 is taken as 0 because of minima. So after substitution we will get pi plus or minus 60 degree as an angle. Next the half power point direction, we will get beta d cos theta half power point direction. When we are substituting the value, we will get pi plus or minus 77.2 degree. So this is what the isotropic sources are increased, side lobe angles, more side lobe information is exists. So these are the angles marked here. So beam width calculation have been found by half power, HPBW is nothing but half power beam width, first null beam width. Half power beam width is equal to theta half power point direction 2 minus half power point direction 1. So that angle is taken as taken, and the difference of that two angles are given as 25.56 degree. And first null beam width, it is theta first null 2 minus theta first null 1, so which is given as 2 into 90 minus 60 degree. First null beam width is calculated as 60 degree. Next, end fire array, same procedure, only the condition is beta d cos theta plus alpha. So this is what the difference for end fire array. So condition number 3, so beta d cos theta minus 1. So same like broadside array, we are going for major lobe direction, minor lobe direction, direction of maxima, direction of minima, half power point direction, as well as direction of maxima, side lobe information. Next, direction of maxima for side lobe, as like broadside array, we are just substituting the values as plus or minus 1 for maxima, 0 for minima. So n psi by 2 sin inverse plus or minus 1. So sin inverse plus or minus 1, we will get 2n plus 1 into pi by 2. So angle psi is equal to 2n plus 1 into pi by n. So if we are substituting n is equal to 4, n equal to 4 is the total number of antennas or total number of isotropic sources. Capital N is equal to 1, D is equal to lambda by 2. If we are substituting this cos inverse plus or minus 3 by 4 plus 1, So 1 minus 3 by 4, 1 plus 3 by 4. So we will get the angle as 75.52 degree. Next, direction of minima. Direction of minima, as usual, we are taking 0. So when we are substituting, angle psi is equal to sine inverse 0 is equal to plus or minus n pi. So 2 n pi by n. So cos theta minimum, when we are calculating the values, we will get cos inverse 1 plus 2 n plus n. So this capital N is nothing but n equal to 1, 2, 3 and 4. Small n is equal to total number of antennas. So the minima direction we will get is 60 degree for n equal to 1. For n equal to 2 we will get 90 degree. N equal to 3 we will get 120 degree. So half power point direction, when x is equal to 1.391, sin x by x table, it gives 1.707, that is 1 by root 2 value. So finally we will get the angle as 38.86 and minus 38.86 degree. So this is what the end fire array radiation pattern, either 0 degree or 180 degree. So the maximum field strength will be. So the beam width calculation is given as half power point beam width as well as first null beam width. So it was substituted. This is what the radiation pattern of a cell phone tower which is radiated in highly populated area. So to highly populated area like metropolitan cities or any urban cities, we need to increase the field strength. So we are going for now n number of isotropic point sources. So one technique is said to be Hansen-Woodyard Array. So it has 4 isotropic sources, and for n equal to 4. So only alpha is equal to beta d plus pi by n. If you are using pi by n, adding pi by n formula, pi by n is equal to 4 isotropic sources, n equal to 4. If you are substituting n equal to 4, so we will get 90 degree plus 45 degree, so that your radiation pattern angle will be increased. This is for 4 point sources. For 8 point sources, same n equal to 8, we will get 180 degree plus 180 degree by 8, you will get 202.5 degree. So 4 point sources and 8 point sources, Hansen-Woodyard array with the addition of pi by n value. So this is what the radiation pattern of broadside array and end fire array. This is the 2D structure and this is what the 3D structure. Now broadside array can be converted to or bidirectional array. Broadside array outcome is bidirectional pattern. Bidirectional pattern can be converted to unidirectional pattern. How? So 2 points, one is which is the identical spacing between the antennas will be kept with respect to lambda by 4 and it is excited with 90 degree. If these two conditions are satisfied, bidirectional radiation pattern can be converted to unidirectional pattern. Hope everyone have understood. Step by step, if you are doing the analysis, we will be understand very much. Thank you.